Interaction that is described by this matrix associated with this is subject to TP violation. To a very good extent, if you replace particles by antiparticles, the physics is the same. But the weak interactions don't really honor that. To a good extent, if you replace physics by its mirror image, you replace left hand by right hand, the physics is the same. Weak interactions don't really honor that. However, the product of the whole operation is honored by the weak interaction to an excellent approximation. But in the 1960s, about a 10 to the minus 3 violation, this combined symmetry was found. And this is associated with this mixing family. It's especially relevant physically because at least some form, this is actually probably more beyond the standard model, that some form of TP violation is needed if one's going to explain why there are more particles than antiparticles in the universe, which is a rather important fact we will see here as well. I want to talk about problems and outlook. So we're never really satisfied. Perhaps we should be, but there's still something to be done. There's still a lot to be done. There's still a lot for your generation to do, because there's clearly something else beyond the standard model, despite the fact that it's so incredibly successful. Okay, any questions so far? Okay. Supposing I want to describe a physical system, it might be elementary particles or it might be some other physical system. It really takes three types of ingredients or things to understand a physical system. One of them is the entity. That is, what are the objects in that system? What are the things you're playing with that you're talking about? Suppose you're talking about Newtonian gravity. What are the entities? Massive objects. What else do you need to know? Interaction, sure. How do they interact? What are the forces? And in this case, we know it's given by the inverse square law. What else do you need to know? Pardon me? That's true. I didn't really have that in mind, but you're correct. You really do need to know initial conditions. But I had something else in mind. Yes. Symmetry? No. No, you're making it too hard. Yes. Yeah, time evolution, or what I was going to say is the response to the forces. What is the set of rules? But you can call it time evolution just as well. And symmetry is actually valid. Too. In this case, it's F equals ma. Now, in particle physics, well, in atomic physics, one would have the same sort of thing. For the entities, one would have electrons and nuclei. For the interactions, you would have Coulomb's law. And for the response, you would have quantum mechanics. Schrodinger's equation. In particle physics, the entities are the elementary particles. I'll call them the fundamental particles. The interactions and relativistic quantum field theory. Relativistic quantum field theory, which you already have studied, is a set of rules rules or the dynamics that determines everything, but you have to supplement it by knowing what the field theory is. You cannot tell an infinite number of field theories, but you have to know what the fields are and what the Lagrange interactions are. And so here we're going to, again in this course, we're going to use this as a framework to talk about what the fundamental things are and fundamental interactions. So, I forgot before I jump into that, let me do one other thing. For relativistic quantum field theory, I simply mean this is simply the union of special relativity and quantum mechanics. So it has relativistic kinematics, it has the possibility to create particle and antiparticle pairs out of energy and so forth. And at any given time, one's description, what is considered fundamental, etc., may be only an approximation, just as this was only an approximation to reality. The standard model is undoubtedly just an approximation also. Let me, however, just stop for a second and just introduce my notation. H bar and C are equal to 1. You can always restore so that means that there's basically everything has units of energy, or energy squared, or 1 over energy, or 1 over energy squared. And you can always restore the other types of units just by remembering that H bar in somebody else's units is 10 to the minus 22 million electron volts seconds, and H bar C is equal to 197 million electron volts times Fermi, and C is 3 times 10 to the 8 centimeters per second. Remember, centimeters, seconds, even electron volts, all these units are just sort of human-based things, and just having to do with how big we are and all that. And this is the real units of nature. Also, I will always use a metric G mu equals +1, -1, -1, -1. Another problem, as you well know, is if you go to any two instructors or two books or something, they always have slightly different conventions and notations and so forth. Okay. Now, so what are the fundamental particles? Well, the fundamental, our notion of what is fundamental changes with time. And so I'm going to first write down what we thought were, or what appeared to be, the fundamental particles in the mid-1960s, before the quark model, early 1960s, I should say. And we now know that these are not truly fundamental, that there's another level beneath them, and there may be others as well. But at this time we had the so-called strongly interacting particles, the ones that feel the strong force, which, for example, combine to make a nucleus. And so these are called hadrons. And there were hundreds and hundreds of them, but the main ones were the proton and neutron, which had spin 1/2, and which make up various combinations of unitary nuclei. And then there were a bunch called the delta resonances, 4 of them. And these have spin 3/2. Then there were, for example, the pions, pi plus, pi minus, and pi 0, 3 of them, which have no spin. Another one called the eta, which also has spin 0. Some others called the rhos plus or minus, rho 0, which have spin 1. And then there are many, many more. And that particle data book, which is this is just a little tiny summary table of it, there's hundreds and hundreds of them listed. Now, most of these, other than the lightest, are what are called resonances, which means they decay very rapidly into lighter particles via strong interactions. And so, for example, the delta plus decays into a proton and pi 0, or it could decay into a neutron and pi plus, etc. The delta, the mass of the proton and neutron, is about 900 38 million electron volts in energy units. The delta has a mass of about 1230 million electron volts. And the decay, so-called width, which is the inverse of its lifetime, is about 120 million electron volts, about 10% of its mass, which means that the lifetime is about 6.6 times 10 to the minus 22 MeV seconds over 120 MeV, so about 6.6 times 10 to the minus 22. 6 times 10 to the minus 24 seconds. So it only lives for 10 to the minus 23 seconds. This is called a resonance. And if you were to actually plot the cross-section, for example, for P-pi-0 scattering, as a function of the center of mass energy, you find that it has a sharp peak at both the mass of this delta and with a width that is given up to a factor of 2 or something by this width, which is the inverse of the lifetime. It's just like any other resonance system in classical mechanics or atomic physics. So incredibly shortly lived. Similarly, the modes decay rapidly. Everything on this chart except the protons, neutrons, and pions. And the pions are about 135 million electron volts in mass. Everything else is a resonance. Yes. Okay, I'm just trying to decide how to respond to that because that would lead to about a 2-hour discussion. The point is, yes, you would take a view and that the proton and neutron and pions were fundamental, and that these resonances are merely short-lived bound states of them. That would be one point of view. However, at the time, most people, going back to the 1950s, people really tried very hard to take that point of view and wrote down field theories with protons, neutrons, and pions as fundamental and tried to treat it exactly that way. Those were never very successful. And by the 60s, people realized that all these other things seemed to be almost identical, similar in properties, except the fact that by the accident of being heavier, they could decay. So it wasn't really clear that you should think of this as a bound state of a proton in pi-0. It merely can decay into it because of the accident of kinematics. So people started thinking about them all as sort of equivalent, and there was a big movement in the 1960s called the bootstrap theory, which actually postulated that none of these things were truly fundamental, but they were all sort of the only self-consistent solutions to general ideas such as unitarity and other such things. And so bootstrapping sort of starting from nothing. That never panned out. And at any rate, we now understand that they're not, and that'll be another board, that these are in fact almost basic quarks. And so that's clearly a much more accurate view. Okay, now a couple of comments about this. First of all, you notice that I put parentheses around some of those groups. That's because I suspect that future symmetry. All the ones that are put together like this actually have very similar masses. The mass difference here is 4 or 5 million electron volts versus an average of 930. And similarly, every other set are very close. And so, in fact, there seems to be no basic difference, I think, because of twins or quadruplets here. And they just come, and some of them are all by themselves. Well, this is famous. But they come into multiplets that are similar, just in the same way that in atomic physics you can have multiplets of states that just, for example, differ in the spin orientation of the electrons or in the 2l plus 1 orbital states. And they're nearly degenerate. These labels, these are electric